and we are back for another session, Military Applications of 3D Printing. We have with us Moisés Domingues from CODI and also Nicolo Gianelli from Stratasys. Stratasys and CODI have been with us presenting one of the main sessions with more viewers, so I hope this will happen again. Nicolo and Moisés, I'll pass the floor to you. Please, go ahead.
Thank you, Francisco. Once again, thanks to you also for the last years too. And I'm here to present also Nicolo. He will make some presentation about additive manufacturing on military defense. He has several experience already, the Airbus and other companies also in aeronautics. He is now embedded on the defense customers and applied additive manufacturing. Once again, thanks, Nicolo, for your time, and please follow. Go ahead.
Hello, good morning from my side. Thank Moisés for introducing me, and happy to be here once again, and hopefully next time in person. This is the last time online. So I'm here. As we know, Stratasys has been here for several years, so you might all know our name. Just for those who are new to Stratasys name, it is the company that invented additive manufacturing 30 years ago, and it's today the biggest one within the polymer additive manufacturing. And we have over 140,000 machines around the world and more than 1,000 patents granted or pending. It means that we keep innovating, and innovation is at the center of our focus. And now we go directly in what's the result today of these 30 years of development. We have improved a lot, so we have introduced several new technologies during the time. And what's good of these is that they are capable of covering the entire development cycle for your product. So we go from prototyping and tooling, where we have PolyJet technology and stereolithography, to prototyping and tooling and production parts with the industrial FDM technology, so filament-based technology. And then we enter into what we call mass production for additive manufacturing with DLP-based technology, Origin P3, and a powder-based technology, which is SAF. We will see later a couple of words more on these technology. What is important, and this is the biggest news of the last years, is software. So through software, we have been able to integrate all our printers in a unique interface, giving the customer the possibility to process their files and to have the machine file ready in few minutes and easily, and also to integrate with the current setup of the manufacturing floor. So it's very important to provide both the hardware and the software, and this is what Stratasys is doing today. Very quickly on the FDM technology, this is our first technology. It's a filament base, and it uses thermoplastic material. We see here on the left a video of how it works briefly, and we see that it's based on the use of model and support material. This is important for what we will see later. Also on the right side, we see a little bit internally into the printer how the material comes. It's in form of canisters, and also it's very important for this technology because it means flexibility and easiness to change between one and the other material. And we will see that it makes possible to access multiple applications through these properties. The range of printers for FDM today is quite broad. So starting from the left, we have the office printers. We call them in this mode, the F123 series. And given the materials that this printer can use, they are suitable and they are used for prototypes and tooling. Still for prototype and tooling, we have the F770, which is the biggest or the largest filament-based machine from Stratasys today. This is a 1 meter wide machine, and it was launched last year. It runs ASA and ABS, so it's sold specifically for prototyping and tooling. On the right, we see the two machines that enables for production, once again, thanks to material. So the Photos 250 and the F900. They are the machines used today by our military customer, by our aerospace customer, automotive, rail, bus, and really advanced industries. And we will see now why they are used for this purpose. Just a couple of words on why an investment on FDM is a good one. First of all, the materials. So FDM, by using real thermoplastics, is capable of delivering materials with superior properties. It can be the mechanical properties, it can be the impact resistance, the thermal, the chemical. Really, every material has its own field of application and enables the customer to fulfill all the requirements. We have seen in the small video and in the small structured design how it works inside. This is an extremely easy to use technology. So you don't have a powder going around, you don't have resins. It's very quick and easy to change between one and the other material. So really, this is easy to use and unattended technology. What our customer appreciate a lot is the return on investment. So when investing in this machine on the right application, the return on investment is typically between 9 and 18 months. So it's a machine that pays itself in very short time. Materials, once again, material is the word that I will say the most today. We have certified materials in these running on these machines. So our materials meet the certification requirements from the aerospace, from rail, from bus, medical, military, biocompatibility, really a lot of different certifications. And here we finally see how we meet all these requirements. So I divided the materials according to their performance, actually. So going up, we increase the mechanical, the thermal, and the chemical performance. We start with the standard plastics. We go up with the engineering plastics, where we find the polycarbonate, the nylon, and all the different blends of nylon that we are able to that we make available to our customer. And we go up to the high performance. Here we find the Ultem family, where we have the, for example, the FST rated materials, the materials that are certified for aerospace, for space, for military. We have the nylon 12CF, which is a nylon with a 35% of carbon fiber, so very strong material from a mechanical standpoint. We have Antero, which is a PEC material, so high chemical and high temperature resistant. At the bottom, you see also that we introduced elastomers. So on the office printer, the F123 family, we have the possibility to print also a TPU. And so we can access all these print applications where we need a flexible material. I said in the beginning, this technology is based on the support and the model material. We have the possibility to use soluble support. So very briefly, it enables to create even more complicated geometries, because we don't need to access manually to the internal part of the component, but we can dissolve the support just by putting it in a solution of water and caustic soda. So again, more freedom and more flexibility to FDM. Last, on material, Stratasys has changed its paradigm on material. So we were closed before, and now we changed to an open paradigm. That means that on the Fortress 450, people will be able to access third-party material, will be able to develop their own material and to tune the parameters of the printer to achieve the best performance of their material. This is especially important in military field, because we know that there can be some niche material that are not developed because they are not for the large market. But with this capability, military customer can develop their own material with their own properties. So this is very important from Stratasys. Second technology, and this is a kind of new one to Stratasys. So it's a digital light processing based technology. We call it P3. And as any DLP technology, it's based on the use of resins and on their polymerization. In this case, thanks to UV light that will be irradiated by a screen to the shape that we want to create. Just a couple of highlights on this machine. This is the machine with the lowest part cost on the market based on DLP. It has a build envelope of 192 on the X, 108 on the Y, and 370 millimeters on the Z. Quality, This machine is capable of delivering the best quality within the resin technologies. So it has a tolerance of plus minus 50 microns. So this is really a game changer in this world of machine. And it has surface quality, which can say it's comparable with the injection molding quality parts. So this is a very powerful machine, especially, and once again, if we look at the material side of this machine. So we see that we have already today more than 10 materials available. And what is good also here is that we are partnering with big polymer manufacturer. You see some names on the right, but the good point is that hundreds of material will come on this technology. What I want to highlight on the left top, we see the 3955. This is a high temperature material, can go around 300 centigrade degrees, and this is FST rated material. So it meets the requirements from the aerospace industry. This is very important because we will see it enables a lot of application with this new technology. The third one that will be that we will see today later in the application is the SAF, so our new powder bed based machine. In this case, we work on powder. We have fluid and we have lamps as a source of energy, and it basically melts the powder to create the part that we want to create. Just a couple of highlights also on this machine. The layer height is 100 microns. We have a size of 315 in X, 208 in Y, and 293 in Z direction. Currently, it works with a PA11 material, but we announced just last week that we are gonna run on this machine also PA12 and a polypropylene. So this is also a machine very reliable and that can deliver a very low cost per part components. From a material standpoint, it's less wide than the other materials, but than the other technologies. But we will see that still it's capable of delivering very important applications for the military industry. Let's talk now about the application. So this is the most important part of the presentation. I introduced a little bit the company, the machines, the materials. Now let's see what we can do for military and for aerospace and defense in general. Our technology enables, of course, to do prototyping. That's the history of additive manufacturing. But today we can place ourselves in production part. We can place ourselves in manufacturing tool and also in the management of spare parts and obsolescence. So that means that, for example, we are able to create tools for, and we will see example, tools for metal forming, tools for thermoforming, tools for polyurethane, for foams, composite layup tools. Really, our materials and our printers enable a wide range of application. The first one that I would like to see today is metal replacement. So we introduced a couple, now we had the pandemic in between, so the timeline is a bit stretched. It was 4 years ago, actually. We introduced 4 years ago the nylon 12 with carbon fiber. So this is a polyamide 12 with 35% of carbon fiber. And differently from the competition, we are able to print it at the full density. So you see in the slide, we can achieve a density higher than 99% in our components. So that means that we can replace metal parts with a material extremely strong, extremely lightweight, and you see 7 times lighter than the equivalent in aluminum. Now I go directly to examples. So we see in this first example on the top, very big end of arm tool. So it was used at the end of a robot to move components, and it was welded steel. On the bottom, we see the substitution, let's say the replacement with nylon 12 CF part, printed with our F900 printer. On the left, we see the economics and the advantages. So we were able to achieve a 61% weight saving, and by that, to reduce the time of the cycle of 20%, round about 20%. Otherwise, you can keep the same cycle time, but you can use a smaller robot with a lower power. So this means a lower investment when you need to buy your robot in your facility. Also on the cost saving, so besides the time, the cycle time or the energy on the robot, you also have direct cost saving on the replacement of the part. So the lowest part, the part on the bottom, was round about 30% cheaper than the previous one made with steel and with welded steel. It was also faster, of course, and so you achieve all the objectives of additive manufacturing: faster, lighter, and cheaper. We see more example here. Once again, nylon 12 CF. On the top, we see CNC holders. So we have components that hold in place our metal part while it's being worked at CNC machines. On the bottom right, we see on the other side, part for part replacement. So we come from directly from the military sector here. It's a naval component. We see on the right the metal part, on the left the nylon 12 CF part done with our Fortus 900 machine. The good point is that you have internal channel here, and once again the possibility of having soluble support is really helpful here, because we printed this component in only one part, and then we had the support dissolved just by putting it into the tank with the water and caustic soda. So with these components, we were able to achieve a cost saving between 50 and 70%. And here, the time advantage is even more, it's even bigger than the previous example, because we were able to have our parts in hours instead of days or weeks. Couple of properties of the material: it's capable of withstanding over 900 bars of compressive strength, and this leads us directly to the next example. So thanks to the compressive strength, we can use our plastic printed part to produce sheet metal. So in this case, this is a sheet metal forming mold. Just a couple of words on this tool. The duration. This tool was able to last more than 500 cycles. So we don't have the same duration of a metal tool, but when we have the need to produce something like 500 parts with this metal shape, and this is typical in military and in aerospace sector, we can use as our nylon 12 CF part to produce the mold and then do the sheet metal forming. Thanks to the compressive strength, we can also do several materials, so aluminum, titanium, steel. Of course, depending on the pressure, we need to, depending on the material, we need to go to lower thickness, because if we have to form 2 millimeters of steel, it's different than forming 2 millimeters of aluminum. So again, here we need to be a good engineer and adapt to their requirements, but this is a very valid solution and extremely faster and lower cost in comparison with the traditional technology. Last example, so we have a couple more for metal replacement, just to say that it's not only about nylon 12 CF, but we can also use all the other materials that we have available on FDM. The example here is Ultra 985, weight reduction from 68 kilograms to 12 kilograms. And then we see what is the advantage in this case. On the lower left picture, we see the operator moving this assembly tool with his hands. So you don't need additional equipment to move it. Once again, this is a quicker and cheaper item to get in comparison with traditional technology. Here we see an example from aerospace, so Boom Aerospace, Boom Supersonic, sorry. On the left, you see a router cutting template, and this was realized with DRAN. So DRAN is a nylon-based material with talc, and it has the lowest coefficient of friction of our material. This means that if you use a tool made with DRAN and then you, by mistake, bump into your part, this will not create any scratch. This is very important from a tool, a very good property, and this is why Boom is using our DRAN material and our printers to produce these kind of templates in their manufacturing chain. This is the last one from the manufacturing, from the metal replacement. I just wanted to underline the capability of reaching high temperature for our materials. So ULTEM 1010 can go up to 213 degrees. You can think about a lot of application. Just one that I brought today is the spraying for thermal procedure of coating. And you see on the top image, this procedure applied to an aeronautic engine. So when you need to do maintenance on an engine and you need to do covers for the areas that don't need to be coated, you can produce the cover with ULTEM 1010. And in this case, you will save the time that was before needed to do the covers with the taping, manual taping actually, and the reference is on the lower left picture. So you save the time and you save the cost associated. Additional advantage, this is a reusable mask, so you don't need to waste it after the first use. So very important in maintenance, repair, and overhaul. Now we go directly to the military. I divided it into three main families: land, naval, and air. We start from land, and we have seen actually a wide use of our system in defense and land application. All the pictures that you see here are slightly modified, I would say, from the real part, because we cannot disclose, of course, the original one. But they have been used on 6 tanks as of today, and our technology have been used, you see, for fire extinguisher bracket or for the storage compartment divider. In this case, we have put in the slide ULTEM 985 because it was the beginning requirements. The requirements were relaxed a little bit, and so this component has been produced now with the nylon 12 CF, and actually it's 2,700 pounds cheaper than the original one. These examples are coming from the UK, so the data are in pounds, but we can easily make the parallel with euro. Going down, we have other examples from the console. For example, we have a screen housing, realized in this case with the TPU, because it was needed to have a flexible component, and also the main periscope housing, again done in TPU because it was needed to be flexible. Again here, very quick time to part. So when you need to repair your component inside the tank, you can do it directly on the field, and you can do it in few hours. So you can reuse the tank or the vehicle immediately. Here I brought a couple of other examples because I wanted to highlight that it's real part replacement. So here you see in the pictures on the left the original part, on the right the equivalent done, and the replacement done with FDM. And very important here is that we have contact with aggressive fluids. So in this case, the metal part was subject to corrosion after a certain period of time. With the plastic one, we have the additional advantage that we don't have corrosion. Going forward, we see the specific quantities for these examples. Sorry, I moved the bar just a second. I had the visual obstructed. So we see the fun of the previous slide here in detail. This is a heat resistant part, so it can go up to above 150 degrees. So it's really fulfilling the requirements from the military field. Cost reduction is between 40 and 90% for the 2 examples that we see in this slide. And once again, this is a metal part replacement. So really, the original one was in metal. The replacement was done with FDM on the field and with lower cost and lower time. Additional example. So we see here the handle of this satellite. The handle is in the lowest part, and on the top you see the satellite communication system. This handle was breaking frequently, so it was necessary, of course, to replace it frequently. And the OEM part was costing $45, and our customer has been able to produce it with ULTEM 985 with a cost of only, let's say, $13. So a huge cost reduction. Additionally, the part is breaking less now, and it's quick when we have this unlikely event of break. We can substitute it very quickly and producing it directly on the field. On the right, we have a couple of examples. So the black one is the cover, and this was realized with the ASA material, and the golden one is in Ultra 985. So also here, depending on the requirements on the part, we use different material to meet those requirements. More example, on the left, we have the flip-top valve on, let me check, this is a T45 Goshawk breathing mask. So this was replaced by the Ultima 9085 black, so it's the black part, black and orange part. And on the right, you see another example with the cost. So this is a mount viewer for the optics of this helmet. And the mounter was, the OEM was producing or actually delivering it for a cost of 102 pounds. And our customer was able to do it with the Ultra 985 in additive manufacturing with only 8 pounds and 45. So also here we had the swap between the Ultra 985 and 912 CF now, because they discovered that there is no specific need for Ultra 985, and so they could even lower the cost of the part and use the advantage of the soluble support that you have with Ultra 985. Going forward and very quickly over naval, we have many more cases coming also for the naval side of defense. So we have, for example, redomi for antennas. So the cover part of the antenna can be produced with our component. We also have a very good behavior from an electromagnetic standpoint. So this can be kept into account when using a polymer instead of a metal. Then we have, for example, air vents, and then if we move in the engine room, we have once again the engine fan, we have the fan housing, and we have the possibility to create, for example, the valve handle in a more ergonomic shape than the original. Need to underline here that the chemical compatibility of FDM material and of thermoplastic in general make them a really good material in this kind of environment. Remember that you are using salty water, you are in a moisty environment, and so rust, corrosion, you avoid these problems by using FDM. Going inside let's say inside the ship, we have seen something outside. We see other example. So, for example, moving from left to right, we see light housing. We see the possibility to create shelves. We see the possibility to substitute the plugs. They break quite often in the ships. They are quite complicated assembly. And when you break one by replacing when you replace it by using the one provided by the OEM, you will need to replace the entire assembly. With additive manufacturing, you can produce just the part that it breaks. So you save once again time and money. And once again, you have materials capable of withstanding the requirements. For example, I didn't say before, we have ESD capable material. So when you need ESD, so more conductive material than the isolant, the insulative one, traditional, you can use ABS ESD or the PEC in the ESD version. So once again, really a lot of flexibility from our system. On the left, you see the possibility also to go in a less noble environment, but still needed on a ship. Toilet cover. And this is an example from the US Air Force, actually, and we will see better explained later. But this is being done also in naval. So people print the replacement of the parts in the toilet with additive manufacturing. Next example is coming from a couple of slides before. Is the valve handle. So here we have, once again, on the left, the picture of the metal parts, the original one, and on the right, the replacement. So clearly the left broke and it was replaced with an Ultim 9085 part. Why Ultim 9085? Because there was the requirement to be FST, so flame retardant, smoke, and toxicity rated. For this part, we were able to reduce the cost by more than 50%. It was also printed in hours, and very important here, the ship was blocked with this valve broken. So it was a real big damage from an economical standpoint. So reducing the time from days to hours was a big advantage for our customer. Just one additional thing, in this case, the material used was Ultem, but once again, if you don't have the requirements for FST rated material, you can look into our wide offer of material and use another one to produce the same part. Going to the last chapter, this is the air. So we go to the origin of aerospace and defense. We come back to aerospace. And we have an example of maintenance, once again, of a military fleet. So the part that you see here is a replacement part for an out-of-production aircraft, which is the B-2 bomber. We see the image on the low left. The component is a cover for a cockpit switch, and it's thought to avoid unintentional activation. So the switch below is covered, and in this case, you avoid to hit it by mistake. This part was not existing from the OEM, so it's an improvement that the US Air Force thought about. So they trusted 3D printing, and they were able to print, and you see the numbers here on the low right of this slide. They used FDM. They printed 20 covers to put on their fleet of B-2 bombers, and the total cost was only $4,000. So it was extremely cheap to maintain the whole fleet of B-52 bombers with this component. Here's the other component that I anticipated before. It's a lettering cover done with Ultem 9085. So here we, of course, don't have the appearance of Ultem 9085 because, and this is another thing that I like to underline, we can always do post-processing to our FDM printed part. So in this case, it was a painted part. So the painting applied was, of course, also FST rated, but we printed the part, we post-processed it, and then it was possible to put it on the aircraft. Let's move on the top of this slide. Cost reduction. Cost reduction is dramatic for this example. So by ordering the toilet cover, we needed to pay, or let's say, sorry, I always use we, but it's the customer actually. The customer needed to pay $10,000. With the 3D printer, with Stratasys 3D printer and materials, they were able to replace it with $300. So it's dramatic decrease. Once again, in this case, Ultem 9085 was used because you have a flying part and you need this part to be flame, smoke, and toxicity rated. So let's remember that we have material FST rated, not only for military, of course, but also for civil aviation. So we can do end-use parts with Ultem 9085 and our printers. Let's go quickly through the last couple of examples. Here we switch technology. So if you remember, in the beginning, I said that we have origin. We have 3955 from Henkel. This is UL 94 V0 rated material. It withstands the FST requirements from the aviation regulation. And so you see an example here. This is a hydraulic cable clamp that is used once again in military on the F-16 fighting Falcon jet. So this part was very cheap and very quick to produce. You see the numbers on the low left, more than 12 parts per month per printer. So this is the potential of this technology in the future. On the right, you see, of course, the demonstration that this is an FST rated material. So the flammability tests were successfully passed by this material. Moving into the drones. So military doesn't mean only military aircraft. It's also about drones. So with our technology, drones is one of the biggest field of application. You see a couple of examples on the low left, a spar, on the right, an antenna bracket. Specifically on the antenna bracket, we were able to reduce the price from $378, which is the price from the OEM, to only $16 by printing it in additive manufacturing. It's a very small part, very low amount of material, $16 with additive, $378 with the OEM, the original replacement. So you see on drones also we have the advantage. Additionally, on drones, we have less requirements from a regulation standpoint. So we can use cheaper materials. We don't need to use the ULTIM, we can use ABS in case it's needed. So really here, the flexibility is even more. We don't limit ourselves to the flying parts. We can also produce ground equipment. So in this case, we needed, or the customer needed, Marshall Aerospace needed to create a component that was able to direct the air to the avionics. So during the maintenance and on the ground, we need to provide cool air to avionics, and they didn't have the right tool. So they were able to print these ground equipment with our printer. And very important in this case, they reduced the weight of the part by 63%. This part is handled by an operator. So reducing the weight makes the operation easy, makes the error less frequent, makes everything better from an operational standpoint. And now we see the last example. So I hope I have been quick enough. Composite tooling. Remember, we have high temperature resistant material. The example here is from the Super Stallion helicopter. The case was a crack on a blade of the helicopter. So you of course have a pressure sensor inside the blade, and when the blade breaks, the pressure drops and the sensor sends an alarm. In this case, it's necessary to replace the blade. Our customer, with our solution, has been able to put in place a different solution. Let's say they did just a repair of the blade. Sorry, I hear a lot of noise in the back. So they did just a repair of the blade instead of buying the whole one, and they used our printed mold in order to do the preform for the composite prepreg. So they printed the preform with ULTIM 95, and they were able to then do the repair of the blade instead of buying the entire blade. This would have cost $210,000 and 160 turnaround time, 160 days turnaround time. So this will be the standard way of repairing or substituting the blade. By using our components for composite tooling, they were able to spend only $15,000 and to repair the blade in 21 days. So a saving of $195,000 per blade, and turnaround time reduced by 140 days. So extremely quick, extremely cheap. Really, this is a game-changing solution for them. This was the last example. So yeah, thanks from my side for listening, and open for Q&A.